Okay, perfect. So, welcome, good morning. Thank you everyone for being here in our fourth Disaster Mobility Data Network. Remember that this is a community practice to advance mobility data for disaster analytics. And here we want to bring together to the table policymakers, emergency managers, data scientists, and researchers to advance this field. Today we have a great agenda. We have human displacements prediction post-disaster, inferring spatio-temporal displacements pattern by Hamish Patten, and current state and plans of the high-resolution statement layer by Andrea Gross from Facebook. Hamish is a theoretical and computational physicist with a PhD in nuclear fusion from the Swiss Institute of Technology Lucerne in Switzerland. Currently a research associate in the Department of Statistics at University of Oxford. He has worked on a broad range of projects, including mortality risk modeling of cardiovascular disease and chronic kidney disease, theoretical ecology and evolution, as well as disaster displacement risk modeling. Hamish also worked for more than 2 years part-time as a volunteer data science research fellow at the Internal Displacement Monitoring Center. Andreas Gross, he's a scientist with a background in complex systems and Facebook's spatial computing team. He currently works on the high-resolution settlement layer and connectivity crisis data on spatial demographic questions. For his PhD, he studied the evolution of dispersal strategies at the University of Würzburg, Germany. He expanded the work on spatial coevolutionary systems as a postdoc at New England Complex System Institute, where he also worked in spatial socioeconomic systems like ethnic violence. He received his diploma in Applied Systems Analysis in the Institute of Applied System Analysis in Augsburg, Germany. Thank you very much for being here, and without further ado, I'll give the screen to Hamish. Also, remember all the questions will be at the end. If you have any, please put them in the chat and we will address them at the end of each presentation or at the end with the open discussion. Thank you very much for being here, and Hamish, the space is yours.
Okay, thank you very much. Also, thanks for the introduction. Oh, that doesn't look like you're seeing my screen. Yes, you are. Okay, good. Okay, so yeah, thanks for the introduction. So I guess this project is something that, because I worked as a sort of a volunteer data scientist for IDMC for just over sort of 2 years. Basically, I just saw a potential gap or sort of something I could work on that I thought that was quite interesting. So today I'm going to talk sort of 5 different topics. I'll talk about disaster displacement modeling. I'll give an overview of sort of what some sort of leading organizations, how they do it. Then I'll talk about how my approach is a little bit different to theirs at least. I'll show some results focusing on Haiti, the earthquake in August. I'm not sure I'm going to have time to talk about vulnerability. I might just quickly gloss over it. I'm going to try and really address the problem of sequential hazard modeling, which hopefully will become clearer later on in the presentation. And then finally, I'll talk about inference on hazard impact. Oh, by the way, we can still hear you, Andy, just in case. Sorry. Okay, so how do sort of leading organizations deal with it? So I've just compared here GDAX and USGS because that's what I've been benchmarking against. So they use something called linear models. So if this is a Haiti earthquake, so this is the hazard intensity and the contour lines, and this background filled contours of sort of density plot is the population. So you see the hardest part of the highest intensity part of the earthquake there also happened to be a densely populated area, which is the worst case scenario, and that's why we're seeing such large loss of life and just damaged buildings, etc. Now, some of the approaches from these 2 organizations is to essentially to calculate the total displacement from an event. They essentially compare regions affected by at least a certain strength or intensity of hazard. So within this purple region, everyone was exposed to at least 5 on the MMI scale in terms of the hazard intensity. here at least 5.5, and here 6, and so on and so forth, right? And obviously these aren't perfect contour lines. I should have really plotted the proper filled contours, but I didn't. So what you can sort of say with expert knowledge is you can sort of hazard a guess of, well, 1 in 1,000 people who are affected by a hazard intensity of at least 5 for earthquakes will be displaced. 1 in 500 for 5.5, 1 in 100, so on and so forth. But what these approaches do is using linear models, what you'll do is you will essentially get rid of these arbitrary, well, not arbitrary, but sort of guesses. And that because you use loads of different historical events, well, you can actually let the data speak for itself. And this gives a total displacement. Now, what I would like you to do is throughout this presentation is question everything I'm doing, everything everyone's doing. So what's the problem with this sort of approach? Well, the first thing is that because you sort of use these sort of statistical models, you can end up with a situation where the number of people displaced is even larger than the actual total population exposed to hazard. Equally, depending on the model you can use, I don't think GDAX or USGS has this problem, but you can also have negative populations displaced, etc. And the other problem is it's zero dimensional. You can only know that there is X number of people displaced. You don't know where they're displaced. You don't know where they're displaced to, etc. And the first half of this presentation will make a focus on how I try to tackle the problem of where people are displaced from, not where they're displaced to. And at the end of this presentation, hopefully, I'll try and show you that by combining different data sources, then you can actually make an inference of both where people are displaced from and where they are displaced to. Okay, most important part for a statistician, physicist, whatever I am, is what's your validation data? What's the observed data that you want to compare with? So here for this global earthquake model, I extracted data from 157 different earthquakes in 47 different countries, so which is quite important because you get a broad demographic. And this is over the past 10 years. So, okay, it's not ideal because it doesn't go further back, but for the data, the plethora of data that we have available at the moment, this is kind of, this is the best that I could come up with. Where is this data? What is this data? So it's a guess of, or an observed estimate of the number of people displaced. So this can be combining number of people in shelters, number of people in hotels, so household surveys, so sort of subsampling the number of people expected to be displaced to family and friends, etc. The next part is from satellite image based data. So Unisat, Unitar, and Copernicus do a fantastic job where after certain hazards, usually those in high intensity and high population exposure, they compare photos of the ground before and after, and they highlight certain buildings for damage. They also denote that damage classification in terms of sort of major damage, minor damage, possible damage, no damage, etc. And for this, we have 270,000 buildings. So that's quite a lot of data. And what does this data do that the other data set doesn't do? Well, it helps you to refine that spatial resolution or spatial accuracy of your predictions of your model. Without these, you could have a large range of different parameterizations to which the model could easily fit. In 20 earthquakes in 14 different countries. Now, just to point out, neither of these data sets are ideal. They're both actually really not ideal in some senses. So this data set, in terms of the total displaced population, it's noisy because you don't know how well that estimate has guessed, essentially, the number of people displaced to family and friends, whether it's missing out certain shelters or certain hotels, etc. Right? So it often is expected to underestimate the displaced population. And then you also have building damage. These sort of satellite image comparisons are only tend to be done in the areas that have the highest hazard intensity. So exactly, so the worst affected areas. So in terms of the areas that are lightly affected, this data set doesn't really cover it. So I'm trying to be as transparent as possible with you, but I'm trying to cover my back as much as possible by using different data sources. And I'll try and throw in some more towards the end of the presentation. Okay, how does it work? So this is an agent-based model, which essentially you layer different data sets one on top of the other, including population and hazard intensity. Now, if we take the same plot as before, what we're actually doing is building a grid set, so gridded data set. So for every grid point, you have the population at that grid point, so usually sort of a square kilometer, something like that. You have the average hazard intensity, and you have some sort of socioeconomic variable, which I can talk about at the end if you want, but it's sort of based on either sort of GDP per capita or the relative wealth index. But I've only just started doing research with the relative wealth index is produced by Facebook Data for Good. Maybe Andy can talk about that later on. Okay, so you have these 50 people at this one specific grid point, and you make your model and you calculate, okay, how many people do we think are displaced? Where it takes out 10 of these people. Well, this is good, but it's just for one earthquake. And what we have is usually you have 4 shocks and aftershocks in the earthquake. So we add on another earthquake, and that says that an extra 5 people are displaced. Now, what's important about these sorts of models is that you can only have the number of people displaced at each grid point as there are people from it, predicted from the population data set. So if there's only 50 people estimated to live there at all, the maximum displacement from that grid set you can have is 50. That's good in some senses, that you don't get out of control displacement numbers. You're not going to get billions estimated from a population that's only 1 million or a couple of million. The bad side is it kind of pins itself, well, so does the other methods from GDAX and USGS, but it's quite dependent upon the quality of the population data, which is basically what I've been battling with this past 2 years or year and a half at least. Okay, the next part is the building damage. So here, I'm sorry, the plot is so hideous. I wanted to be able to display it to you in the best way possible, and I failed to do that. But it's essentially each blob here is a different building assessed for damage by Unisat, Unitar, and Copernicus, and you have different classifications. So in this example, with these 1,400 buildings, there's only 4 different categories. Okay, and for each grid point, for each building, not grid point, we've moved away from grid points here, and we're working on single individual building estimates. We calculate what the hazard intensity is at that data point, at that location, socioeconomic parameters, and then you predict its sort of damage level, which is actually a continuous variable, a continuous value, but then you actually you treat it in kind of a classification regression problem, and you can map one-to-one to different damage classifications. Now, why is this also important? If you're looking forward to what do we want to do with this in the future? Well, actually, if we extract data, so buildings from OpenStreetMaps, which I've done recently for the Haiti earthquake, but I'm not going to show you in today's presentation, and you start estimating the damage likelihood or damage probability for each building, then you can also make estimates on the number of buildings damaged. And this can be compared with other data sets as well, which I'll talk about later. So results. I was going to show you a slide on benchmarking to USGS and GDAX, but it's really uninteresting, so I've included it at the end. I say this uninteresting. I say that because I'm a scientist, so what I want to do is give you the most concrete results possible, talking about different statistical metrics, but equally I want to make this presentation understandable, so I kind of had the worst of both worlds. So we can talk about that at the end. But shock horror, this model produces results that compared to the GDAX and USGS risk alert, these were sort of 10 times more accurate at correlating with the number of people displaced than GDAX and USGS alert scores. Now, just an asterisk there, GDAX and USGS actually make their risk scores based upon economic cost and loss of life. So we're not comparing one for one, but these two should really correlate well with displacement as well. So either I'm calling for a sort of new model from both organizations that is explicitly adapted to displacement, or you could try, you could consider using ODDRIN, which is the code that I'm presenting today. Okay. Now, the best part of this code is, as I said, you get this mapping components, this spatial distribution of the number of people displaced. So just ignore the top for the moment. On the bottom is the number of people actually displaced now. And I kept the contours of the hazard intensity. So you see certain regions where there are a large number of people that are predicted to be displaced. And that's because there was such high hazard intensity, because there was such densely populated areas, etc., and also socioeconomic factors. Now, you can compare this and validate this with different data sets. Now, this is from the SEDIMA situation report. I think it's number 11. I'm sorry, I forgot which one it was now, but one of the situation reports. Now, you can't really compare like for like here, which is why I'm doing a deeper dive, and I'm actually communicating with a couple of different staff members from SEDIMA. But essentially, this is combining people displaced from and people displaced to in this map. So it's not really the same thing, because what I've covered here, what I'm showing you here is the displaced from locations. So this sort of will correlate with where the buildings were damaged or where people have moved away from, right? Okay. Just to make a comparison between values we actually do know, so the total number of people estimated as displaced from SEDIMA based on building damage assessment is around 220,000. And this value is actually lower than what I would expect, because the building damages, there was something like 50,000 buildings that were completely destroyed. And that therefore assumes that it's sort of like 4 point whatever to people per house in terms of the average household size. And for Haiti, I think it's actually larger than that. So I think the value is larger than this, but that's obviously my opinion, which I'm not an expert in this sort of field. Okay, expected value predicted is around 270,000. It corresponds roughly, I mean, for statistical methods, this is a fairly reasonable prediction. And I wanted to be transparent with you, everyone in the audience here today, there's a lower and an upper bound, and it's pretty large. I mean, we're talking about half a million people range here, which is not ideal, but I'd rather be open and transparent about it than not. And this uncertainty is getting narrower and narrower the more I get to work on this problem. So trying different population data sets, etc., right? Different validation techniques. In terms of the 1,400 buildings, around 77.2% of buildings were correctly classified in terms of minor, major, and no damage. We can come back to this at the end, but one point that I really want to mention is you can validate this entire model in different ways. You can validate the displacement, so what's the total number of people displaced per country, per region, etc. And if you've got on-ground data, then that's just fantastic. The other thing is damaged buildings. So you can take the total number of damaged buildings by extracting buildings from OpenStreetMaps or Google Earth, and predict how many buildings you expect to be displaced, damaged, and then you can compare that to the actual value. Number of damaged buildings per country, per region, and then, as I've shown already, comparing it to UNISAT and Copernicus. They're manual by hand estimates of damaged buildings. Unfortunately, vulnerability, I'm not really going to get to cover it, but one thing is essentially you can use the predicted values and the difference between the actual observed value to infer correlations with different variables, maybe gross national income or basic access to sanitation. If the value is higher than expected, maybe it's because the country has a high unemployment rate, population growth, etc. You can extract loads of indicators from the World Bank and make this correlation. And voila, the top three. Honestly, we can go through this at the end because I really like this work, but I know it's not really that relevant to mobility data. for this meeting. The top three is sort of population growth, GDP per capita, and access to basic sanitation. Okay, sequential housing modeling. We're almost towards the end here. So looking at Cyclone and Harold passing over Vanuatu in April last year. Now, if I were to say to you, what is the displacement if you were to look or use this map in your calculation? So what I've already done wrong here is that I've asked you to predict on something where, well, what's the speed? How long did it take to go over Vanuatu? And what you find in all sorts of codes that exist, whether it's GDAX, Risk Alert Score, or Climada, they're all really good methods, but they don't really, at least not to my awareness, they don't account for the fact that if a cyclone traveled 2 times slower, there's obviously going to be a larger displacement that would occur than if it were to go 2 times faster than the actual cyclone path. So this is looking at sustained versus maximum wind speed. And this, I think it's quite important, and I included it in my work. So before you saw it in foreshocks and aftershocks of earthquakes, and here I use the hourly maximum surface wind speed throughout the entire thing, which is actually computationally extremely expensive, but I thought it was worth it. So what did I do? I compared with 12,000 different buildings assessed for damage from Unisat and Copernicus. This covers the 1st to the 10th of April, which is like hundreds and almost 1,000 different timestamps. So it's quite computationally expensive. Still ran in less than a day, but actually I can't remember how long it took to run. Anyway, so here on the right you have the displaced population, so internally displaced person stock. And here you see for different islands, they have different values. And this is obviously due to hazard intensity, socioeconomic factors, and population density. Now, what I want to talk about over the next few slides is, well, what can we do more than this? Rather than just leaving it as is, how can we use existing data sets to make further inference on, for example, temporal trends? What's the rate of return of populations? Okay, so we can combine the Facebook data for good, so the disaster mapping, where you have for each island here is a different plot, and you have it disaggregated by sex. You have the number of people displaced along the y-axis and the decay in the number of people displaced in time. Sorry, decay. The rate of return of people per day since the start of, or since the, I can't remember when, maybe the first few days after the cyclone passed. Okay, so what you can do is you can couple this to the predictions, right? And you can separate female to male displaced population. You can compare day 0 to day 40, right? And so I didn't say earlier, but that data set that I just showed you from Facebook Data Good is actually a simulated data set. It's not the actual data set because we're working on it. I'm working on it with Eugenia Giraldi, who works for Facebook Data for Good. And we're doing a deep dive on a couple of different hazards. Now, what we can also do is make a really hideously low quality, horrible video showing the rate of return of people to different islands. And it's just sort of to show you that you can have this spatial temporal patterns. And this is not from predictive, this isn't entirely predictive analytics. It's combining the best quality data sets that we have to shed light on things. Okay. Final point. What's the difference between the information you can get from evacuation shelters and from damaged buildings? If this is the volcanic eruption on St. Vincent, April this year, what do the two data sets infer? If I knew how many people were located at different evacuation shelters, and I also knew locations of damaged buildings and their classification of building damage, what can I learn from each of these data sets? Well, one of them talks about displaced to. People are obviously displaced to evacuation shelters. And there are certain data sets that will shed light on this. XDR, an example of this is Facebook Data for Good, like I'm using. An example of call detail records is FlowMinder. They do some really, really, really good quality work on this. Household surveys, shelter occupation, hotel occupation, displaced from is the same as before. So Facebook Data for Good, Flowminder, household surveys, which you can also get surveys done by Facebook themselves, which is super interesting. We'll talk about both, which I forgot to mention, and building damage. Okay. To conclude, agent-based models give a deeper understanding, allow for spatial distributions of displaced populations. This is, from what I understand, the first ever displacement face spatial mapping. And when you combine it with the different data sources, the first ever displacement spatio-temporal mapping. This, I didn't cover it that much. Systemic vulnerability can sort of be inferred from the a large sort of historical data analysis. I covered sequential hazard modeling and why I think it's important. Tell me if you think I'm wrong. And I talked about combining complementary observed data sources. To conclude, myself and Justin Giletti, who's from the Red Cross, so IFRC, are hosting a roundtable event on the 22nd of November. And so Andrew Schroeder, who I think is in the audience, I'm pretty sure is in the audience, will also be one of the panelists for this conference. Please sign up. I would absolutely love for people to attend. And we're going to talk about 3 different themes, but all of them reunified under the topic of statistics in the humanitarian sector disasters. We got some fantastic presentations expected. Please, please, please join. You can find it on the statistics, so Department of Statistics for the University of Oxford website. And I can also, I might post this PDF on the group afterwards. Thank you very much. Are there any questions? Oh, sorry. Actually, we're not asking questions, I think. Sorry, Andy.
No, don't worry. I was going to say that let's wait till the end. So now let's have Andy's presentation. Thank you very much for your presentation. And if you are able to put the link of the event here in the chat so everyone can see it, that would be helpful.
Excellent. Yeah, thanks, Andy.
Hi guys, can you all see my screen? Can you hear me?
Yes.
Okay, let's go into presentation mode. I hope this works. Hi. Yeah, thanks for having me. My name is Andy. I'm the tech lead on the high resolution settlement layer, which is the public version of our population density layer that we've been working on since 2014. And I've been working on and off on it, but like as of about 1.5 years ago, I took over the work again. And so now I'm going to tell you a little bit about what the current, how we do it, basically as a short rundown, what we're currently doing and what our future plans are for the next version that is in the works. So what we're doing is we use computer vision models, convolutional neural nets that we run across high resolution satellite images. And all of our results basically are contingent on the quality of the satellite image data that we're getting. Then we partner with CSIN at Columbia University who collect global census data, and we combine those two to derive a population density data set. Here's a short animation of where we can see how we're transitioning from like the GPW4 that existed before we started working on this. Here we zoom into Kenya, and then we transition over to what we're doing and what we're publishing right now. But as I said, all of this depends on the quality of our input data. We recently found some really bad data in Nigeria, for example. So, and we always need to be concerned about strategies of circumnavigating this. And this is what I'm going to be talking about. So in version 1, we currently have data on more than 190 countries and political units on the Humanitarian Data Exchange and on AWS as our cloud optimized geotiffs. And that was just, here you see a map of not what we publish, but what we have internally. because for countries and regions with severe political tension, when the local policy team says you cannot publish this data, we will not, right? So there's always going to be regions where we do not publish the data. But so this map is slightly out of date because we recently published Norway, Sweden, and Finland for the first time. Again, a problem with the input data, where the input data used to be so bad because so our vendor is Maxar. Normally they do a very good job, but in the northern latitudes and on the very southern latitudes, the way they warp their imagery across their virtual model of the Earth is they use a digital elevation model, and that model is severely outdated. And they only recently have started to pull in a more accurate model and stretch their imagery across their model of the globe a little bit more accurately. And what version 1 does is it just uniformly distributes people in the census area across the buildings we identify. So in areas where the satellite imagery is bad, we detect too few buildings, the population per building will be too high. In other areas where we have census undercounting, for example, the population will be too low. But we still compare very, very favorably compared to other data sets that are out there. So where our input data is good, we have usually very high accuracy, precision, and recall. But then again, there's always problem countries. So Nigeria, and especially around Lagos, is one of them. So people especially people from IHME, the Institutes of Health Metrics and Evaluation, they've done a great job comparing our data sets in some places. In this case here is Bioko Island, where they have a full household enumeration, and where we scored best overall. Other data sets like Landscan, for example, they do a better job in dense urban areas than we do in assigning more people to larger buildings, and that's something we're working on in the next version. That is that's currently in the works. So yeah, here you just see like one example from India, where it's like we're pretty confident in our results. Like if you see such a clear image, then our results are very, very good. We even match like round huts in Tanzania, because Tanzania was one of our first countries that we were working on, and we handpicked a lot of training samples to match all sorts of buildings. What currently, so to get around that problem of like bad input data, we started integrating data from OpenStreetMap, and we trained an additional classifier. So very often when we have bad input data, what happens to, so our classifier gives us a score between 0 and 1 that a tile contains a building, and a tile is about 32 by 32 meters. And we determine then, with the help of human labelers, we determine a threshold above which in this specific area, we should consider something a building or not. Like, was that a true detection or not? However, when the input data is bad, our human labelers, they cannot distinguish a true positive from a false positive very often. And so what happens is that our thresholds sink too low and we get too many false positives. And we had that problem in Pakistan, for example. We have that problem in Scandinavia, where because of image artifacts in the Maxar image data, you sort of get like these really, it looks like badly compressed JPEG images where you have like these blocky borders, and those look like straight lines and squares to our algorithm, and that gives it a high probability that there is a building, but then it turns out to be deciduous forest in the middle of nowhere. But so when we get these high amounts of false positives, to compensate for that, we trained an additional classifier that is based on the ELOS digital surface model. And that looks at, does that location look more urban or more rural? Does this look like a settlement or not? And that helps us weed out like a large percentage of our false positives. So with OSM, we densify dense urban areas. And with a digital surface classifier, we weed out false positives mostly in rural areas, but also we help maintain samples in the dense urban areas. What we're trying to add for version 2 is estimates of building volume and of building type. This is all very early stages. Wherever we have good polygon data, for example, the estimates work really well. Where we do not, we only can provide like very coarse estimates of building volume, where we are subtracting two different surface models. One is a terrain model and the other one is a surface model. So yeah, so version 1.5 is currently rolling out. As I said, for version 2, we're planning on providing estimates of what we think is the residential building volume. And we're moving from 30 meters per pixel to 10 meters per pixel to make our volume estimates more accurate. Why is this hard? Well, it's hard to extract building height just poorly from like a single satellite image. That's not what we're ultimately trying to do, but we're trying to infer building polygons where they don't exist, and then use a variety of sources to estimate building height. But yeah, to train this, good 3D models that are coming from a variety of sources are hard to come by. So in the US, we have a sufficient number of building models, but in other countries, that information is much more scarce. So if you guys know of any sources, please let me know. That will greatly help our work. But then also modeling the density per unit residential building volume is also a challenge, where like there's some buildings that by their very type and their very nature contain a higher density of people than other buildings. And tuning these models locally is going to be a challenge. And survey data isn't the easiest to come by for this. And of course, we're trying to do this on a global scale. We're starting in a few test areas, but eventually we want to move this to a global scale. So at the very basic, as I mentioned, we have the surface model and the terrain model that we're subtracting and then sharpen it to building polygons. But we're also trying to add other data sources like LiDAR and other publicly available higher resolution data sources. We're investigating building up a Sentinel SAR radar interferometry pipeline, which makes us more independent of like clouds, which is a big problem for Maxar, because one of the reasons we have outdated or bad data is because of clouds, and they have to reach far back in time to pull in and stitch into their data the most recent cloud-free image that they found for this area. But also we can infer building shapes from crowdsourced GPS signals, where we're saying, well, from this position, if you're not seeing satellite X, Y, and Z, but you're seeing satellite A, B, and C, then we know that the line to X, Y, and Z is blocked, whereas to A, B, and C it is open. And from this, over time, we can infer like the rough outlines of buildings. And also like open geometry data wherever it's available. For building type estimation, it's going to be a lot more challenging than the building volume estimation. So we're also going to take a variety of approaches into account. So like the neighborhood structure classification, pretty much similar to what Oak Ridge does with their neighborhood type classification. But also this is the first time we're trying to bring in Facebook data from Facebook user data, which is then anonymized locations of like how often has this location be classified as a work location, or how often has this location be classified as a home location, for example. And then by that mix, we can start to make inferences about whether or not this is likely a commercial building, a residential building, or a mix in between. Yeah, that was all for me. Please let me know if you have questions.
Thank you very much, Andy. If there is any questions from the public for Andy or from Hamish, please let us know. Yes, Rachel, go.
Yeah, thank you very much. These were really exciting presentations. I had a question because, again, a lot of this data is you're looking at a lot of quantitative data points. And I wanted to inquire whether you're looking at doing kind of other qualitative research or gathering other information points, particularly on kind of the last segment you looked at about looking at the size of houses and how that would correlate to number of residents, for example. So just curious to hear if you're looking at kind of other data collection to answer some of those questions. Thanks.
Yeah, absolutely. We're trying to use as many input data sets and verification data sets that we can get access to. And we're relying heavily on our partners from CSIN, from Columbia University, to help us with like microcensus data and others, and also our partners from the World Bank, although very often the bank cannot share their locations with us, but we can provide them with our estimates and have them verify it or tell us how wrong we are.
Can I just take the opportunity to respond to one of the questions in the chat and then follow up with actually a question of my own to Andy? There's just a question about like what population layers do I use? So I actually use a combination of CDAX, sometimes, rarely now, the high resolution settlement layer, and then also World Bank. And this follows into my question. The reason why I use World Bank is for countries like China, the quality of World Bank, there's certain articles that I found in doing a literature review that sort of said that for China, CDAC population compared to the World Bank, World POP, sorry, is actually sort of like 50% worse in predicting population density. And so here's my question. Is there a list of countries that are not included? Because I think China isn't included in the HRSL, right?
Correct. So we have not done anything in China. I can like put my presentation, I don't know. Yeah, I can send you the presentation. You can see the map but we don't have a list of what we haven't published. We only, like on HDX, you can see, and from the cogs on AWS, when you pull down the cogs, you get everything basically that we have. You can also subset it to 10 degree by 10 degree tiles, which is the native format they come in, and the cog is just a virtual raster file that binds them all together.
Okay, cool. Yeah, thank you.
And we're using the same input data that World POP also uses. Like everybody uses seasons data for this, and World POP, we're starting a new collaboration with World POP on getting around some of the bad census data. For DRC, for example, the most recent census is from 1970, I believe. So that is more than 50 years old. And So we have a lot of like demographic projections don't work if you have now house locations that where the census used to have 0, right? So you cannot forward project from 0. And so we're trying to find algorithms to make us more independent from like really bad and outdated census data. But that is ongoing research, and that's also research that WorldPop does. And WorldPop has, I believe, like more than 26 academic institutions involved. And so we're trying to start a new collaboration on this.
I have a question for Hamish, if I may.
Yeah, hi, Nick.
Hi, Hamish. Fantastic work, and I'd love to spend some time reading through it. My question is digging into what have you learned about the causal factors that may explain the amount of people displaced from a given location. And I was particularly wondering, have you done a kind of exercise where you would look at, let's say, earthquakes of similar intensity that affected areas at differing income levels? And the hypothesis to me would be that, let's say, urban areas which have higher income and have been able to take some preparedness measures and have good building codes are going to withstand an earthquake of a given intensity with fewer people being displaced. I wonder, empirically, have you looked into that?
Yeah, 1 second. Okay, so in terms of they're fantastic questions, and this I'm really glad that you asked these questions, because these are the questions that I asked myself, and I spent the last sort of 6 months really trying to narrow down on these 2 problems specifically. So in terms of the causal factors, I mean, yes, this is this is the work I've been I tried to show in the sort of vulnerability side of things. In those 2 slides that I covered there, I would like to do invest a lot more time in that. But it's essentially, so when your prediction is out by a certain factor, as I said, you can use sort of these correlation techniques to infer what was actually the cause, or what is the highest likelihood, which variable has the highest likelihood that it was the causal factor on why that area or that entire earthquake had a larger displacement than another earthquake. So I actually, in another presentation I gave not that long ago, I compared sort of the Japan 2018 earthquake to the Afghanistan 2015 earthquake. And they had 5.3 million people who were affected by at least sort of 5.5 on the Richter scale earthquake. And yet Afghanistan had like 55,000 people displaced, whereas Japan had less than 3,000 observed as displaced, right? Which is also another thing, right? And by the fact that I've combined 157 different earthquakes allows this sort of development of causal factors. So I'm currently using Bayesian networks, so directed acyclical graphs, to try and infer some sort of causality. And these, to be honest, these are national variables such as population growth and so on and so forth. If we're talking about subnational, which is your second question, subnational indicators, the problem is really data sets. You need to cover a broad demographic. So you need a large number of countries, some of them rich GDP, poor GDP, high exposure to earthquakes, low exposure, etc., right? In order to get a proper understanding of what's going on. And in terms of the data sets that cover a lot of these different countries, these 47 different countries, it's really difficult to get anything. So the 2 that I used up till now are population density. So exactly as you were saying, urban-rural divide. And this parameter was centered on 300 people per square kilometer, which is the definition, I think, of a urban area. Anyway, And then the other parameter I used was GDP per capita, but it's super low resolution. It's the Kumu Nature, what's it called? Scientific Data article, 2018. It's kind of low resolution, but it's what I've got at the moment. As I said in my presentation, can't wait to use the relative wealth index. For the moment, the study I will do over the next month or so will use the relative wealth index, but obviously this only applies to low to mid GDP countries. So it's limited in demographic, who it speaks for at the moment. So that was a very long answer, I'm sorry, but it's a question that I'm really interested in. So my bias led me to talk for forever. Apologies.
Thank you very much. Now we have a question from Alexei.
Yes, hello everyone, and thank you for the impressive presentation. Hi Andy, hi Andy, and nice to see you again. My question is for you, Andy, about you mentioned that Facebook data were really helpful to be able to label or to make sure that this is residential or workplace. And my question is that after COVID-19 pandemic, and we all know that the mentality of remote work has changed, and does that affect the accuracy, and what were actually the main challenge like you faced and building that accuracy measurement?
So yeah, certainly that has affected us greatly, because like this is part of a different team's work. And they're adjusting their models, but also this data will go away, because there will be, Facebook is trying to move away a little bit from using location data in their, like in the app in general. And so that data will become more sparser and sparser over time, and it's probably going to get deprecated early next year anyway. So we're already looking for alternative data sources. But yeah, that's not something we can bank on in the long run.
Thank you so much, Andy.
Great, now we have a question from Samira.
Hi, thanks so much for the great presentation. Hi, Hamish. Sorry, the question is not for you. I know Hamish, so for everyone else wondering. I have a question to Andy. I'm an economist, so I'm very interested in causality, and I'm glad Nick already kind of touched upon that. For causality analysis, almost always do you need temporal information. So I was wondering, how confident are you that you can produce layers, let's say, I don't know, maybe realistic 10-year intervals that can be used to track population changes over time at a high spatial resolution. Also, I myself, I'm super interested in the DRC, so I'm very excited to see that you guys are working on something on the Congo. Very, very excited about that, just because, you know, the data is not really there. So that's very exciting on a personal level, but the question is, how confident are you in being able to produce something that has temporal resolution in not within like 50-year intervals, but you know, something I don't know, 5 to 10 years.
Yeah, we get this question a lot, and we're currently only trying to predict the status quo, basically, or like maybe like 5 years in the future. But our current estimates are 2020 estimates. It is very hard. So that we had a collaboration proposal with the German Aerospace Agency. They do the World. They just renamed the global urban footprint to something else. But yeah, so what we wanted to do with them, unfortunately, this is mired by like German legal technicalities. We wanted to take HSL as it is now, and then the German Aerospace Agency is really good at working with low resolution data, and low resolution data like Landsat is available historically. And what we wanted to do is take our current mask and then go backwards in time to see how has a place grown historically. We currently have no plans on pulling this off in the near future, unless we're 2 people working on this at Facebook. So we're super tiny for this kind of stuff. Unless we can grow our team by probably like 5-fold, we could be tackling this again and dig out that plan. So there used to be that plan, but it's currently, it's not going anywhere. So the German Aerospace Agency's legal department says our licensing terms are more open and incompatible with Google Earth Engine's ones, which they're more restrictive. And so the DLR, the German Aerospace Agency, uses Google Earth Engine for their compute. So they say we can't combine those data sets because like Facebook cannot guarantee the restrictiveness that GEE, the Google Earth Engine, imposes.
I'm not sure if that helps. I'm also German, so I'm very much aware of the huge amount of bureaucracy that comes with being a German or doing anything German. But if that's any consolation, there's definitely demand. I'm sure I'm not just speaking for myself. So if at some point you find a way to supply it, I'm sure I'm quite certain there's already demand.
No, it's on our wish list. We always wanted that could be one of the input factors that make our census projections much more accurate, right? If we can track local settlement growth, then historically, because like if the season does the census forward projection to project to the current estimated national total, right? So, but that doesn't help you when you have like these 2 settlements in 2 different census tracts that historically grew very differently. That doesn't help us take that into account. And if we could be tracking the local settlement growth, that would make our census projections much, much more accurate. It's definitely on our wish list, but like with the current staffing, it's not going to happen anytime soon.
Okay, thank you very much. And there is one last question, both for Hamish and Andy, from Giovanni. Do you think that the mobile network operator data could be integrated into your studies? And what would be the main pros and cons about this?
I think Andy, I think you already replied in the chat to from your side. I'll just quickly mention mine, and then Andy, if you want to come in. I think for me, it's super interesting. It's really hard to be automated. The amount of time it takes to actually get access to the data is not on a time frame that I ideally would like to work on. So that's kind of it. And actually, to be fair, even the data itself, you need some really rigorous statistical methods, which is why I'm so impressed with organizations like Flowminder, who have hired some extremely talented people to do that sort of inference for them. So I think it's a really tough analysis to make. And then coupling that further on to my work, it's very difficult. I think I respect anyone who really goes through that.
Yeah, I replied in the chat. So we tried working with MNOs. Facebook works with a lot of MNOs, but the data for good side, when there is a chance that this data may influence something public, that is not just between 2 business partners, then MNOs become very, very hesitant in providing you with any kind of data. Even for like very severe humanitarian crisis, like the first Ebola crisis in Liberia, Guinea, and Sierra Leone, we collaborated with like 2 MNOs and for their cell tower locations, so that we could link up emergency treatment units to the internet. That was like the toughest negotiations I've ever witnessed. I mean, it was really hard.
Thank you very much. Thank you both of our great speakers for your presentations, and thank you all for being here. Just a quick reminder for the next Disaster Mobility Data Network meeting will be on November 23. It's going to be on Tuesday instead of Thursday. It's going to be in the afternoon. And also our last meeting for the year, it's going to be on December 16 with the topic Data Ethics and Privacy. Thank you all for being here. And if you have any doubts, please feel free to reach me. And let's keep in touch. Bye.
Bye.